Okay, let's move on to section 2 on UDP. So for the transport layer, they figure out that they need to provide end-to-end services through the application layer, through the application program. However, there are applications who expect much from the transport layer, but there are also applications who expect very little from the transport layer. And there are some applications who does not want the transport layer to do much. Say, for example, if you have VoIP, voice over IP, which we will see in the next chapter on chapter 6 for voice over IP. Voice over IP is in chapter 1 we have said that voice over IP is hard real-time application, right? Compared to streaming, streaming is soft real-time, right? And because the reason why streaming is soft real-time is because it's mostly unidirectional, but voice over IP is bidirectional. So you have real-time traffic in each direction, and you need to interact with each other. So it's hard real-time. So the voice over IP is hard real-time, but the streaming is sub real-time. So, so voice over IP would not expect error control from the transport layer. The voice over IP would just need checksum. Well, it needs error control, very limited error control. It needs checksum to detect the error, but it does not expect to retransmit. The packet, if the packet is much delayed, fine, drop it. If the packet is lost, fine, forget it. I don't want to retransmit because the retransmission will be too late. Consider I'm talking to you, and some packets are lost, some voice sample are lost. If it's retransmitted, probably the voice sample which are in the same time period has been played out already. So your transmission, it doesn't make sense to play it now because the voice segment has been played and some sample has been lost, and you retransmit it, and I don't need it now because I can't play your sample. I can play the late sample. Okay, so so for voice over IP, it does not expect retransmission from the transport layer. However, for file transfer, for email transfer, for web browsing, you need retransmission. You need to, if it's lost, retransmit it. If it's late, you wait until you get it. So you need a transport layer that would do retransmission to recover the error. And so you will see that we put that kind of reliable transport into TCP, but we put unreliable transport as UDP. So that's why UDP is designed to be unreliable. So you can say that, okay, if we just want to have best of the breed, so let's do TCP only. Forget about UDP. We don't need it. No, it's incorrect. We need UDP for some application, particularly for two kind of application. One is the hard real-time application. We definitely need UDP. Another kind is for peer-to-peer applications, which pump a lot of queries to a lot of destinations. So in P2P, you know, you want to find something and download something. So what it does is two stages. One, the first stage is send a lot of queries to a lot of destinations, a lot of hosts to ask, do you have this? do you have this? So he asked a lot of people, but within, but just one shot. I just asked them. I talked to 1,000 hosts. I talked to 1,000 hosts, asking them whether they have this data. And some of them reply me. I don't care if all of them reply me. I don't care. If I ask 1,000 and there are 500 replied, fine. For those 500 who didn't reply, I don't care. Forget about them. I got 500 replies. I look at them and I see to whom I want to get the data. Perhaps I pick 1, or perhaps I pick 5 or 10 to download the data. So for those queries, I would just use UDP. I don't want to set up the connection. Okay, I want to use one single socket. Then I would use one single socket. I don't want to create 1,000 sockets, one for each of the destination. No, I just want to use one single socket to talk with 1,000 people, 1,000 hosts, one socket. Okay. And then I got 500 replies back, and from those 500, I filter out and then figure out I need to talk with 5 of them. 5 of them. Then for those 5 of them, I would set up TCP connection with them to download the data. Now the data download needs to be error-free, so I need to use TCP. But for query, I don't care much. Okay, but I need to do a lot, so I use UDP. Okay, so that's why you need both UDP and TCP, especially in P2P applications. Okay, so UDP is simple. It does 2 things only. One is port multiplexing, so you provide UDP port. So again, TCP provide TCP port and UDP provide UDP port. And they all have 16-bit port number field in the header. And so if you have a port number of 80, you need to be aware whether it's TCP 80 or UDP 80. It's different. It's different. In the kernel, it would differentiate whether this segment should be sent to UDP port number 80 or TCP port number 80. And some applications, there are indeed some applications, we will see that in chapter 6. There are some applications they write on 2 port number. I don't remember which one. They could accept request from through TCP port and also request through the same UDP port, the same port number, but actually they are different. So for that application server, they would need to bind themselves onto 2 ports. One is say port 21. Okay, I need to bind myself to UDP port number 21 and also TCP port 21, port number 21. Okay. So they do. So UDP does port multiplexing. It provides port number. So it should be UDP here, not TCP. It should be UDP. And the second thing it does is error checksum, the checksum. Okay, so only 2 things: port number, source port number, destination port number, and checksum. Similar to IP address, you need source address and also destination address. Now, the port number, you need source port number and destination port number. Because you might have 2 hosts with 1 process per host talking to each other. So you need a port number for each of them. Here it says that UDP is suitable for real-time traffic. Why? And I mentioned that retransmission is meaningless in such application, especially hard real time. So no per-flow integrity needed. And you don't do flow control here for such real-time application, because the bit rate of real-time application should be determined by the codec. If the codec say the codec wants to generate 256 kbit per second, and you say you want to flow control the rate, the stream to 128 kbit per second, then you are going to create 50% packet loss. So you don't want to, if the codec decides to pump this fast, you shouldn't do flow control on them. And the better way is to change the codec behavior. In fact, if you see recent application, most of them use the so-called adaptive codec. Adaptive codec, meaning that the codec will be adapted to the network condition. If the network condition is quite congested, not enough, the bandwidth, the available bandwidth is not much, then the codec will generate a bit rate which is smaller. And usually those they use those adaptive codec, they would use a layered coding, the so-called layered, different layers, layered coding, meaning say for an image, I would the basic layer, the second layer, third layer. The upper layer will be something to refine the image, but not as critical. But the lower layer image will be much more important. So if I have more bandwidth, I would have more layers generated and transported. But if the bandwidth is not much, I would have fewer layers generated. So I still, if the network condition is not good, the bandwidth is not much, then I still see the image. I still see the video, but the quality is not as good compared to if I have abundant bandwidth and I could, the adaptive codec can pump all layers of video images, then the quality will be very good. So either way, we should let the codec be adaptive instead of try to flow control the traffic generated by codec. Once it's pumped from the codec, it's decided, the bit rate has been decided, and you shouldn't do much flow control on them. So you will see that flow control should be applied to what? Non-real-time application, such as file transfer, web browsing. You can do that to do flow control, congestion control. But for real-time, you don't. So real-time should be riding on top of UDP, yes. A pair, a process pair. Oh, let's say, so if you, so for example, if this is a packet destined to a web server, then you would have a destination port number of 80. And then the source port number will be the client's port number, the client program on another host. It will usually, the client port number will be something large with larger number, say tens of thousands. Okay, which will be picked by the kernel. It's a random, it's a port number dynamically picked by the kernel. The kernel decided for that client. The client does not need to specify which port number I want to use. The client just call the kernel, and the kernel will generate a port number for the client. However, if you are a server, you need to pick a port number you want to bind to. You tell the kernel, okay, I want to bind myself to port 125. Okay, and the kernel will reserve 125 for this particular server process. Okay, so I'm saying it's a pair. It's a pair. There's a term called socket pair. A socket pair is combining 5 tuples. One is source IP address, destination IP address, source port number, destination port number, and protocol ID. The reason you need this is because you might have TCP port, TCP socket or UDP socket, and you need to use a protocol ID to differentiate whether it's TCP or UDP. That's called 5 tuple. Okay, and not just real-time application. I mentioned that P2P is another large group of application that would need UDP in order to send a large amount of queries. Okay, and we have seen port number, and how about checksum? The checksum is calculated UDP. There's an open source implementation, UDP and TCP checksum, and it would check header, TCP UDP, the transport header, and also the application data. So it would check both. And these functions, they are constructed for more efficient calculation of the checksum. And the IP checksum, the checksum at the IP header, it only checks the IP header. So it only depends on this. But for this, it checks the transport and also application.